record as well. Okay, so thanks very much for everyone for coming. So it's a great pleasure, Kansei Inamura from Tokyo University, ISSP, and he'll be telling us about fusion surface models. Take it away.
Thank you for the introduction, and thank you for giving me this opportunity to give a talk at this wonderful seminar series. So today I'm going to talk about what I call fusion surface models, which are 2+1 dimensional quantum lattice models constructed from fusion 2 categories. And this talk is based on a joint work with Kantaro Omori. So if you are interested in the technical details, you can find our paper on archive here. So let me first summarize the main results of our paper. So in our paper, we constructed a large family of 2+1 dimensional quantum lattice models by using the data of a fusion 2 category. So given a fusion 2 category, we can construct a lot of 2+1 dimensional lattice models from this fusion 2 category. And we call these models the fusion surface models. In principle, we can define the fusion surface models on an arbitrarily 2-dimensional lattice. But in this talk, just for simplicity, we will only consider the fusion surface models on the honeycomb lattice. And in this case, the state space and the Hamiltonian of this model can be expressed in terms of fusion diagrams of this form. And I will elaborate on this point later in this talk. And an important feature of this model is that the symmetry of the model is described by the input fusion 2 category. So this means that we can construct a lot of 2+1D lattice models from fusion 2 category, and this fusion 2 category describes the symmetry of the models. And the symmetry described by this fusion 2 category is a very general finite symmetry in 2+1 dimensions, which include any finite group symmetries with any anomalies. And an interesting example of this fusion 2 category symmetry is the symmetry of anyons. So the fusion surface models can have microscopic symmetries of anyons, which are described by modular tensor categories, or MTC for short. So, and this MTC symmetry can describe chiral topological phases. So this suggests that the fusion surface models with these symmetries might be natural candidates for chiral topological phases on the lattice. But for now, the dynamics of these models remains unclear because generically this model is not solvable. So we need a further study to see whether these models can indeed realize these phases or not. So, so this is the short summary of this talk. And the main subject of this talk is, of course, generalized symmetries. So let me begin with a brief introduction to this subject. But since many of you are very familiar with this notion, I will be very brief here. So, but anyway, let's begin. So from a modern point of view, the symmetry of a physical system is described by the algebraic structure of topological defects. So this means that if a physical system has some topological defects, then we say that this physical system has some symmetry. And this symmetry is described by the algebraic structure of these defects. So for example, if a physical system has an ordinary symmetry, then the corresponding topological defects are group-like. But here the point is that the topological defects of a physical system may not be group-like in general. And even in that case, we can think of the existence of these defects as the symmetry. So, and the reason why we call this symmetry is that the symmetry defined in this way can do what an ordinary symmetry can do. So, for example, if we have a topological defect, then we can define the symmetry action by inserting the topological defect along the spatial direction, as shown in this left figure. So here the vertical direction is the time direction, and the horizontal direction is the spatial direction. On the other hand, if we insert a topological defect along the time direction, then this defines the twisted boundary condition. So in this way, we can understand the twisted boundary condition and the symmetry action on the equal footing by using the topological defects. And from this point of view, the conventional symmetry can be understood as the symmetry generated by codimension 1 invertible topological defects. But more generally, we can consider more general symmetries generated by more general topological defects, and such symmetries are called generalized symmetries. So for generalized symmetries, the corresponding topological defects can have various codimensions. For example, we can think about one-dimensional topological lines in a 2+1 dimensional spacetime. So these topological lines have codimension 2. And the symmetry generated by such higher codimensional defects are called higher form symmetries. So this is one possible generalization of a conventional symmetry. And another generalization is to relax the invertibility. So in general, topological defects can be non-invertible, and we can consider the symmetries generated by such non-invertible defects. And in particular, when the topological defects are non-invertible, then their fusion rules are non-group-like. So if we fuse topological defects A and B, then we get the sum of topological defects. And here NABC is a non-negative integer, which is the number of topological defects C contained in the fusion of A and B. And this non-negative integer is called the fusion coefficient. So and the symmetry generated by such non-invertible defects are called non-invertible symmetries. So this is another generalization. But in the most general case, we can consider the mixtures of the higher form symmetries and the non-invertible symmetries. And such symmetries are called, such symmetries are mathematically described by higher categories. So the main goal of this talk is to construct 2+1 dimensional concrete lattice models with finite generalized symmetries, which are described by fusion 2 categories. These are special examples of higher categories. So here is the outline. So in this talk, we first review the construction of 1+1 dimensional quantum lattice models that are known as the anion chain models. So these are lattice models with finite generalized symmetries described by fusion 1 categories. And then we will generalize this construction to 1 higher dimensions. Namely, we will construct 2+1 dimensional lattice models that we call fusion surface models. And the symmetries of these lattice models are described by fusion 2 categories, which are higher versions of fusion 1 categories. And finally, we will briefly discuss some relations of these lattice models to topological field series in 1 higher dimensions, which are called symmetry TFTs. So more specifically, we will see that the fusion surface models and anion chain models can be naturally obtained by the symmetry TFT construction. So let me begin with 1+1 dimensions as a warm-up. So in 1+1 dimensions, the symmetry of a physical system is generated by topological lines and their topological junctions. In principle, we can consider the symmetry generated by infinitely many topological defects, but here we will only consider symmetries generated by finitely many topological defects. So for example, we will not consider continuous symmetries, such as U1 symmetries or SU2 symmetries, etc., but we will only consider finite symmetries. And it is known that finitely many topological defects in 1+1 dimensions form a mathematical structure known as the fusion 1 category. So this means that finite generalized symmetry in 1+1 dimensions are generally described by fusion 1 categories. And for this reason, finite symmetries in 1+1 dimensions are called fusion 1 category symmetries. So these are very general finite symmetries in 1+1 dimensions. And there are many interesting examples, such as anomalous finite group symmetries and the Krammer-Swannian self-duality of the Ising CFT, or more general symmetries of rational conformal field series, etc. So what is a fusion 1 category? So basically, fusion 1 category is just a mathematical framework to describe topological lines in 1+1 dimensions. But more concretely speaking, we can describe the basic data of a fusion 1 category as follows. So the first datum is a set of topological lines, which are also called objects in the category theory. And we will use this category theoretic terminology throughout this talk. And when a topological line is indecomposable, namely when a topological line cannot be written as a direct sum of other topological lines, then this topological line is called a simple object. And these simple objects are denoted by small letters A, B, C, etc. And here, the number of simple objects is finite, and any topological line can be written as a finite direct sum of these simple objects. And the second datum is a set of topological junctions of topological lines. And these topological junctions are called morphisms. And the most fundamental ingredients or building blocks of these topological junctions are trivalent junctions, because any topological junction can be decomposed into a bunch of trivalent junctions. And the set of trivalent junctions of topological lines A, B, C is denoted by Hom A tensor B, comma C. And this is a complex vector space of dimension n A, B, C. So this means that the number of linearly independent trivalent junctions is equal to the number of the fusion coefficient n A, B, C. So, and pictorially, this trivalent junction can be represented by this fusion diagram. And this fusion diagram is allowed if and only if NABC is greater than 0. Or in other words, this fusion diagram is possible if and only if C is contained in the fusion of A and B. And here I want to emphasize that the fusion rules of topological lines are completely encoded in the trivalent junctions. This is because fusion rules can be completely characterized by this fusion coefficient, but this fusion coefficient is just the number of independent trivalent junctions. So if we count the number of independent trivalent junctions, then we can reconstruct the fusion rules. So in this sense, the fusion rules are encoded in the trivalent junctions. And the last datum is a set of complex numbers that are called F symbols. And these complex numbers describe the crossing relations of topological lines, as shown in this equation. So here the F symbols appear as a coefficient on the right-hand side. And these F symbols must satisfy some consistency conditions known as the pentagon equation. So basically, a fusion 1 category is just the set of topological lines and the set of topological junctions of these topological lines and the set of complex numbers called F symbols. And these algebraic data describe finite symmetries in 1+1 dimensions. So now let's construct 1+1 dimensional lattice models with these symmetries. So, and the lattice model that we are going to construct is known as the anyon chain model. So in order to define the anyon chain model, we first choose a fusion 1 category C, which is going to be the symmetry of the model. So we are going to construct the anyon chain model with symmetry C. And in order to define the state space, we also choose a single object, which is denoted by rho. And this object can be chosen arbitrarily. So for example, this object rho may or may not be a simple object. And from these input data, we can define the state space of the anyon chain model as follows. So the state space H of this model is a vector space that is spanned by the fusion diagram of this form. So each fusion diagram defines a basis of this state space, and any state can be written as a linear combination of these fusion diagrams. And here, these vertical legs are labeled by the chosen object rho, and this is not a dynamical variable. On the other hand, on these horizontal legs, horizontal edges, and trivalent vertices, we have simple objects and basis morphisms respectively. And they are the dynamical variables of this model. So the dynamical variables of this model are simple objects on the horizontal edges and the basis morphisms on the vertices. In particular, these dynamical variables are only on this horizontal line. And here, I want to mention that configurations of these dynamical variables are highly constrained by the fusion rules. This is because these trivalent junctions are allowed if and only if they are compatible with the fusion rules. So for example, the simple object gamma I minus 1 has to be a fusion channel of gamma I and rho because we have a trivalent junction here. So this implies that the configurations of dynamical variables on the adjacent edges cannot be chosen independently. So in other words, the state space of this model cannot be written as a tensor product of local state spaces. So this is a bit weird situation, but nevertheless, this vector space H is completely well defined as a state space of a physical model. So this is a state space. And in order to define the Hamiltonian of this model, we also choose another input data, which is a morphism phi from rho tensor rho to itself. So here rho is the objects that we chose in the previous slide. And the rho tensor rho is the set of morphisms from rho tensor rho to itself. So in particular, this is a finite dimensional vector space. And for each element of this finite dimensional vector space, we can write down the corresponding Hamiltonian of this model. So in this sense, this vector space can be regarded as a parameter space of this model because for each element of this vector space, we have a corresponding lattice model. And pictorially, this morphism phi can be written as a box with two incoming legs and two outgoing legs. And this morphism phi can be decomposed into two trivalent junctions as shown in this equation. So here on the right-hand side, we have the summation over all the possible simple objects A, that is the label of this middle edge. And we are also taking the sum over all the possible trivalent junctions here. And the coefficient WA mu nu is an arbitrarily complex number, and this becomes a parameter of the model. And once we choose this morphism phi, we can define the Hamiltonian H of phi by the sum of local operators Hi of phi. And the action of this local operator Hi of phi is defined by the composition of this morphism phi. So this is the definition of the Hamiltonian. And if we substitute this expression into here, then this Hamiltonian looks like the right-hand side of this equation. So what this operator does is to insert a topological line A between two adjacent vertical legs, and then take the sum over all the possible trivalent junctions mu and nu for fixed A, and then finally take the sum over all the possible A's with some coefficient W. And then by doing the F move around here and here, we end up with the final expression. So in this last expression, this F symbol comes from the F move around the left vertices, and this F symbol comes from the F move around the right vertices. And in this expression, I am a bit sloppy about the indices of these F symbols, and that's what I mean by this tilde. But it is not difficult to restore the indices of these F symbols correctly. So in the end, what we found is that the matrix element of this Hamiltonian is given by the sum of parameter W times FF star. So the basic structure of this Hamiltonian is determined by F symbol. But in addition to this, we also have many parameters that we can choose freely. And because of these three parameters, the anion chain model can realize various interesting phases of matter. So this completes the definition of the lattice model. But so far, we have not cared about the unitarity of the model. So this model is in general non-unitary. But it turns out that if we choose the parameters W appropriately, then this model can become unitary. More specifically, if we assume that the F symbols of the fusion 1 category satisfies the so-called tetrahedral symmetry, then we can show that the Hamiltonian of this model becomes Hermitian if we choose the parameters W so that this equality holds. So here, this A bar, nu bar denotes the duals of A mu nu respectively. And what this equality says is that our Hamiltonian should contain this term and this term with the weight W and W star. So if we flip the orientation of this middle edge, then the coefficient should become the complex conjugation. And if this condition is satisfied, then the Hamiltonian that we define here becomes Hermitian. And therefore the model becomes unitary. And I want to emphasize that due to this condition, the number of independent parameters reduces roughly by 1/2, but nevertheless, we still have many parameters that we can choose freely. And remarkably, the symmetry of this model is described by the input fusion 1 category. The symmetry action is defined by the fusion of topological lines with the fusion diagram that represents states. And again, this symmetry action can be expressed in terms of F symbols very explicitly, but we will not do it here. And this symmetry action automatically commutes with the Hamiltonian due to the pentagon equation. We can check this very explicitly by writing down this symmetry action using F symbols, but more intuitively, we can understand this commutativity from the fact that the symmetry acts from above, while the Hamiltonian acts from below. And the commutativity between these two actions automatically follows from the definition of the fusion 1 category. So this shows that the anion chain model has a fusion 1 category symmetry C. And in this way, we can systematically construct 1+1 dimensional lattice models with general finite symmetry. So before moving on to 2+1 dimensions, I have several remarks on this lattice model. So the first remark is that, as I already mentioned, this state space H does not admit a tensor product decomposition. So it cannot be written as a tensor product of local state spaces. But nevertheless, we can always embed this state space H into a larger state space that admits a tensor product decomposition. And the projection from this larger vector space to the state space of our model is achieved dynamically or energetically by adding some local penalty terms to the Hamiltonian. And this local penalty terms gives a large energy to a state if the configuration of the dynamical variables do not obey the fusion rules. So from this point of view, the fusion 1 category symmetry can be regarded as an emergent symmetry that appears below the energy scale set by the penalty terms. So in this context, there is not much difference between emergent symmetries and exact symmetries. Because on one hand, if we insist that the state space should admit tensor product decomposition, then the fusion 1 category symmetry becomes emergent symmetry. But on the other hand, if we allow the state space that does not admit the tensor product decomposition, then this fusion 1 category symmetry becomes exact symmetry. And we can take whichever point of view we want. And the similar comments also apply to the fusion surface models that we will discuss next. So now let's move on to 2+1D. And even in 2+1 dimensions, what we will do is almost the same as what we did in 1+1 dimensions. So with that being said, let me first introduce fusion two-category symmetries. So in 2+1 dimensions, the symmetry of a physical system is generated by topological surfaces, topological lines, and their topological junctions. And in particular, when the number of these defects is finite, then they form a mathematical structure called fusion two-category. So this means that finite generalized symmetry in 2+1 dimensions are generally described by fusion two categories. And therefore, finite generalized symmetries in 2+1 dimensions should be called fusion two-category symmetries. And these are very general symmetries in 2+1 dimensions. And examples include anomalous finite group symmetries and anomalous finite two-group symmetries, and also non-invertible one-form symmetries, etc. And among these examples, non-invertible one-form symmetries are particularly important in condensed matter physics because these symmetries describe the symmetries of anyons in topologically ordered phases. And I will come back to this point later.
So,
and the basic structure of a
do these anion models that you previously described, do they see the orientation of space-time?
I assume the space-time is oriented.
Okay, thank you. I mean, so you might want to probably embellish fusion category with some extra adjectives like spherical.
Yes, we assume that the fusion category is spherical. Yes, sphericality is necessary.
So what precisely is the place in these lattice models where the spherical structure enters?
I'm sorry, I'm not sure.
Okay, yeah.
But the construction of the 3D track-zero TFT depends on the spherical structure. And I derived the anion chain model from the track-zero TFT in our paper. So in that sense, we need to impose the sphericality. But but it's not clear in what I talked in a previous slide. Yeah.
Thank you.
Another question in the chat, still on the one category. If one builds a 2+1D model with fusion one category symmetries, does that recover the Levin-Wen string net construction?
Yes, our model includes Levin-Wen model. Can I move on?
Yeah, there's now a discussion ensuing on this particular question. I think you'll get to that at the very end, no? When you're discussing sort of the relation also to SymTFT.
Yes. So if there are no more questions, can I move on?
Yeah, please continue.
Yes. So, so the basic structure of a fusion two category is very similar to the basic structure of a fusion one category. So basically, the fusion two category consists of the following data. So the first data is the set of topological surfaces, which are also called objects. And indecomposable topological surfaces are called simple objects. And these are denoted by capital letters X, Y, Z, etc. And the second data is the set of topological interfaces of topological surfaces. And these are one-dimensional objects. And these one-dimensional objects are called one-morphisms. And when a topological interface is indecomposable, then it is called a simple one-morphism. And these simple one-morphisms are denoted by small letters A, B, C. And the third data is the set of topological junctions of topological interfaces. And since topological interfaces are one-dimensional objects, their topological junctions are zero-dimensional objects. And these zero-dimensional objects are called two morphisms. And pictorially, these one morphisms and two morphisms can be represented by fusion diagrams. So for example, this left figure represents a one morphism A, which is a topological interface of topological surfaces X, Y, and Z. And similarly, this right figure represents a two morphism, mu, which is a topological junction of topological interfaces A, B, C, and D. And the last datum is a set of complex numbers called Kansei symbols. So these are very natural generalizations of the F symbols in a fusion 1 category. And just as the F symbols describe the crossing relations of topological lines, these Kansei symbols describe the crossing relations of topological surfaces, as shown in this equation. So the Kansei symbols appear here. And these Kansei symbols must satisfy a very complicated consistency conditions, just like F symbols. But this time, the consistency condition is a commutative diagram not on a pentagon, but on a polytope, which is called a Stashev polytope. So the consistency condition on the Kansei symbols are very complicated, but nevertheless, these Kansei symbols are just complex numbers that satisfy some consistency conditions. So basically, a fusion 2 category just consists of the set of topological surfaces, the set of topological interfaces of surfaces, and the set of topological junctions of the interfaces, and the set of complex numbers called Kansei symbols. And these algebraic data describe finite symmetries in 2+1D. And what we want to do in the rest of this talk is to construct concrete lattice models with these symmetries.
I have a question at this point. So in the case of the fusion 1 category, there's a physical argument why the F symbol has to be some number or faces when we do an F move. And the physical argument in the context of, say, quantum field theory or CFT is based on, say, radial quantizing the configuration around the F move. Now, here in the context of fusion 2 category, I understand this is the mathematical setup, but in a physical setup, can you give us some intuition or explanation why the Z has to be a C number rather than some more general operator when I perform such a move in a concrete 2+1D lattice or quantum field theory?
Now physically, this equality means that in any correlation functions, we can replace this configuration of topological defects by the configuration of topological defects on the right-hand side. So this is an equality of correlation functions. So that,
yes, yeah, I understand the statement, but I guess I'm asking, why do we expect such an equality to be true in physical correlation function with Z being some complex numbers?
Yeah, that's a difficult question.
Okay, that's fine. I was just curious. I'm sure it's correct. I just want to understand the physical argument, something generalizing the radial quantization argument for the fusion 1 category.
To be honest, I am not aware of the physical argument even in 1+1D.
In 1+1D, the argument I will give is that you draw a little circle around the F move. Say for simplicity, let's say we're in a CFT. Then the circle prepares a state for you. And by assuming that you have a unique identity operator, the state on the left and the right have to be proportional to each other. And that's the reason why the F symbol has to be a number. But anyways, yeah, I was just wondering if there's a quick physical argument here.
Yeah, I'm sorry, I don't have any physical argument.
No, that's okay. Thank you.
Yeah, thank you for the question. So we want to construct the 2+1D lattice models with these symmetries. But before going into details of the lattice models, I want to introduce some technical terms that are necessary to describe the lattice models. So first of all, we say that simple objects, X and Y, are connected to each other if and only if there exists a morphism between these two objects. So pictorially, this means that simple objects X and Y are connected if there exists a topological interface between topological surfaces X and Y. And an important point is that this one morphism between simple objects X and Y is not necessarily an isomorphism. So this means that the simple objects X and Y can be connected to each other, even if they are not isomorphic to each other. So this is in contrast to the situation in a fusion 1 category, because in a fusion 1 category, two simple objects are connected to each other if and only if they are isomorphic to each other. But in a fusion 2 category, this is not the case. And indeed, every condensation defect in a fusion 2 category is connected to the trivial defect, because condensation defects can have gapped boundaries, topological boundaries, which are topological interfaces of condensation defects and a trivial defect. But not every condensation defect is isomorphic to the trivial defect. So this means that simple objects can be connected to each other even if they are not isomorphic to each other. And the set of simple objects connected to a simple object X is called the connected component of X. And the set of representatives of the connected components of a fusion 2 category C is denoted by pi 0 C. So each element of this set pi 0 C is a simple object chosen from each connected component. So in particular, the number of elements of the set pi 0 C is equal to the number of connected components. And we can equally say that this pi 0 C is the set of all simple objects modulo condensation. This is because two simple objects in the same connected components are related by the condensation. So choosing a simple object from each connected component is equivalent to modding out the condensation. And we will use this set pi 0 C in the description of the lattice model. So with this mathematical background, we can now describe the 2+1D lattice models with fusion 2 category symmetries. And we call this model fusion surface model. So in order to define the fusion surface model, we first choose a fusion 2 category C. And this is going to be the symmetry of the model. And in addition to this, in order to define the state space, we also choose 3 objects, rho, sigma, lambda, and 2 one-morphisms, F and G. So in the case of a fusion 1 category, or in the case of any on-chain model, we only need to choose single object. But in the case of fusion surface model, we need to choose 3 objects and 2 one-morphisms. And pictorially, these objects, rho, sigma, lambda, are represented by these red surface, blue surface, and green surface. And similarly, these one-morphisms F and G are represented by topological interfaces of these topological surfaces. And from this input data, we can define the state space of the fusion surface model. And the definition of the state space can be divided into 2 steps. So as the first step, we first define the vector space H, which is the vector space spanned by the fusion diagrams of this form. So this vector space H is a straightforward generalization of the state space of the any on-chain model. And as we can see from this figure, this fusion diagram consists of a bunch of topological surfaces and topological interfaces that we choose here. And these are not dynamical variables of this model. But on the other hand, the dynamical variables are living on this top surface, which looks like a honeycomb lattice. So more specifically, the dynamical variables are simple objects on the plaquettes and simple one-morphisms on the edges and the basis 2 morphisms on the vertices. And here the simple object on each plaquette takes values in the set pi 0 C, which is the set of all simple objects modulo condensation. So this means that we do not use condensation defects as a dynamical variable. So this point is a bit technical, but I think this is worth mentioning because there's no counterpart in 1+1D. So this is a new feature in 2+1 dimensions. And although this vector space H is a straightforward generalization of the Anion chain model, Anion chain state space, it turns out that it is not a good idea to use this vector space H as the state space of the model. So instead of using this vector space, we define the state space of the model by a specific subspace of the vector space H.
I have
Yes.
a question. So since you want to label the objects by the pi0, no, which is okay, is there some property of the model which makes the labeling consistent in such? I mean, if I would choose two objects which are in the same pi0, no, the state should be the same, right? That's so. Is there some property of the state space that ensures that if I create an interface which maps between the two guys, you have the same state? To me, it's not obvious.
So sorry, could you say again?
Yeah, go back one slide, please. Can you hear me?
Sorry, could you say again?
Yes. Can you go back one slide?
Yes.
Okay. So here you label the simple objects by elements of pi0 of C, no?
Yes.
Okay. Is it obvious that this definition of the state space is invariant if I choose different representatives inside the classes in pi0?
I think, I'm not sure, but I think the family of lattice models obtained by this construction is invariant under the choice of representatives.
Okay. Okay, yeah,
But
don't
I'm
worry.
not sure.
It's not obvious to see from the definition, but it's okay. Probably it is.
Maybe it's not obvious. But
Okay, yeah,
no
worries.
Thank you. So the state space of our model is obtained by applying some projectors to the original state space, original vector space H. So this vector space H0 is a subspace of H such that the local operator BP is equal to 1 on all the brackets. And here BP is a local projector. And actually, this is a Levy-Wien-Bracket operator that is defined by this diagrammatic equation. And it is easy to see that this Levy-Wien-Bracket operator is a local commuting projector, and therefore this expression does make sense. And there are several reasons why we should use this state space H0 rather than the original vector space H. And the main reason is that the Hamiltonian that we will define in the next slide is not well defined on the entire state space, but well defined only on this projected state space H0. So, and I will say a few more words about this in the next slide. So this is the state space, and in order to define the Hamiltonian, we also choose another input data, which is a two-morphism phi. And this two-morphism is given by the sum of the two morphisms defined by this fusion diagram with some coefficient W. So here, we are taking the sum over all the possible labels of the topological surface that we insert here. And we are also taking the sum over all the possible topological interfaces and topological junctions. And the coefficient W is an arbitrarily complex number, and this becomes the parameter of the model. So we have many parameters that we can choose freely. And once we choose this morphism phi, we can define the Hamiltonian H of phi by the sum of local operators HP of phi. And the action of this local operator HP of phi is defined by the composition of this two morphism phi. So the definition of this Hamiltonian is completely parallel to the definition of the anion chain Hamiltonian. The Hamiltonian is just defined by the composition of morphism phi. But as I already mentioned, this Hamiltonian is well defined only on the projected state space H0. And the reason is very subtle, and I cannot tell you the details in this talk, but basically this comes from the fact that we do not use the condensation defects in the definition of the state space.
Sorry, I actually missed, why are you not using condensation defects in the definition of the state space? What's the motivation
Because
for this?
the motivation is that condensation defect is not a fundamental object in the fusion 2 category because they can be derived from other line operators.
But
But
they're still,
more
you know,
technically,
yeah. If you
more
were to include
technically,
them, maybe you could then define the Hamiltonian also on the full space.
yes, I think
projection.
it's possible. But the more technical reason is that we derived this Hamiltonian from the 4D symmetry TFT.
Mhm.
And this symmetry TFT can be constructed without using condensation defects. And that's the reason why we don't have condensation defects in our lattice model.
But the symmetry TFT also can give rise to condensation defects, right?
In the original formulation by Douglas-Reuter, they also used the condensation defects.
Mhm.
But after the paper by Douglas and Reuter, the Kevin Walker provided the systematic way to construct 4D Douglas-Reuter TFT without using condensation defects. And I use that formulation. And that
There's no
formulation,
reason why that is sort of, physically it seems it's, there's no reason why you should not include them, right? Both in the bulk construction as well as on the boundary, on this 2+1D boundary.
yes, you are right. But
I wonder whether in general condensation defect, number of condensation defect may be infinity.
Yes.
So that's may be some trouble.
But I think in 2+1D, you still probably can get away with restricting to some condensation defects. Like, for example, the one thing I would like to actually see is, for example, rep Z2, 2rep Z2, all the surfaces are condensation, right? So then on these plaquettes, you basically have nothing, right, on these faces, on X. Is that true? Will you discuss this example? The 2rep Z2 fusion category symmetry?
I think 2rep Z2, the simple objects of 2rep Z2 are all condensation defects.
That's right.
True.
And so basically then on these faces, you don't have anything at all. You just have these edges and the vertices.
Yes, you are right. Yes.
Yes. So you kind of reduced it to sort of a lines and local operator problem. And I just wonder whether you could actually include the condensation defects and write down some model, including the condensation of the one form symmetry in that case. And then the Hamiltonian would be the one that you actually wrote down and would be all defined. Anyway, you can discuss this afterwards. I think you'll get to the sim TFT later. So I'll ask you again.
Yes, thank you. So, I defined.
Actually, can I ask a question about the projector?
Yes.
So is it the case that if you don't project into H0, that some of the symmetry operators won't be topological?
You're right.
Okay, I see.
Okay,
so that's kind of some motivation to want to project.
This is another motivation. Yes.
I see. Okay, thank you.
Thank you. So we define the Hamiltonian of the diffusion surface model by this diagrammatic equation. And this Hamiltonian can also be written in terms of F symbols very explicitly due to this equality. So here, this right-hand side is obtained by fusing the topological surface X into the plaquette of this honeycomb lattice. But in this fusion process, we need to do the 10J move around each vertex. And that's the reason why we have the product of tangent symbols on the right-hand side. So each tangent symbol comes from each vertex. And here I am also sloppy about the indices of these tangent symbols. And I am also sloppy about some numerical factors that are related to the quantum dimensions. But basically, the matrix element of this Hamiltonian is just given by the product of tangent symbols multiplied by some parameters that we can choose here. So, and again, if we assume that these tangent symbols satisfies some four simplex symmetry, which is a natural generalization of the tetrahedral symmetry, then we can show that the Hamiltonian becomes Hermitian if we choose the parameters so that they satisfy this condition. So this unitarity condition is completely analogous to the unitarity condition of the anyon chain model. And we also have many parameters that we can choose freely. So, and remarkably, the symmetry of this lattice model is described by fusion 2 category C that we used as the input. And the symmetry action is defined by the fusion of topological surfaces or topological lines, as shown in this figures. And this action automatically commutes with the Hamiltonian because symmetry acts from above while the Hamiltonian acts from below. So this shows that the Hamiltonian, the fusion surface model has a fusion 2 category symmetry.
One quick question. So can the yellow surface be a condensation defect?
Yes.
I see. Thank you.
But then when it is a condensation defect, you then automatically mod it out again because, right, you're looking at these plaquettes only modular condensation.
Yes.
The state space
condensation
basically already removes them then automatically. You say it's trivial.
Yes. Yes. So if we fuse the condensation defect to the plaquette, then the plaquette variable becomes a condensation defect. But there is a canonical way to identify this condensation defect to the representative that we choose, only on this state space H0.
But does that mean the condensation defect acts trivially on every state in your projected Hilbert space?
No, a condensation defect can act non-trivially on the edge variables.
I see.
On the edges, right? But not on the faces.
I see.
Yes. So in this way, we can systematically construct 2+1D lattice models with general symmetry. And this model may look very weird or complicated, but it turns out that this model includes various interesting examples. So let's see a few examples here. The first example is the fusion surface model with an anomalous finite group symmetry. So as a fusion 2 category, this symmetry is described by 2-vec G omega, where G is a finite group and omega is a focal cycle on G. More specifically, the basic data of this fusion 2 category can be described as follows. So first of all simple objects of this fusion 2 category are invertible. That means that pi 0 C is equal to G. This is because this symmetry is invertible symmetry. And since this symmetry is a zero form symmetry, there are no non-trivial 1 morphisms, and there are no non-trivial 2 morphisms as well. And the tangent symbols of this fusion 2 category are completely determined by the focal cycle omega, which describes the anomaly of this finite group symmetry. And in order to obtain the fusion surface models with this symmetry, we need to choose the input objects rho, sigma, lambda. And there are many possible choices. But here, for simplicity, we choose these objects to the sum of the simple objects, all the simple objects. And in this case, the state space of this model becomes a product of local state spaces. And here, the local state space on each plaquette is just the regular representation of a finite group G. So this shows that the fusion surface model, in this case, reduces to an ordinary spin model where each spin lives on a plaquette of the honeycomb lattice, and it takes values in a finite group G. So this is an ordinary G-valued spin model. And this G-valued spin model is guaranteed to have an enormous finite group symmetry by construction. Do you have some questions?
Oh yeah, just a quick sanity check. But when omega is a non-trivial class, the yellow surface is not an on-site symmetry, right?
Yes, yellow surface is not on-site.
Thank you.
So the second example is the non-invertible one-form symmetry. And here, usually non-invertible one-form symmetry is a braided fusion 1 category, which is denoted by B. But as a fusion 2 category, this symmetry is described by a 2 category mod B, which is a 2 category of B modulo categories. But physically, this is just a condensation completion of a braided fusion 1 category B. So this means that all simple objects of this fusion 2 category are condensation defects. So pi 0c is just a single element set. And 1 morphisms and 2 morphisms of this fusion 2 category form a braided fusion 1 category B. And this non-invertible one-form symmetry is particularly important when this B is a modular tensor category, because in this case, this symmetry describes the symmetry generated by anyons. And usually, this modular tensor category symmetry is an emergent symmetry that appears only in the low energy limit of topologically ordered phases. And from this, in this context, a topological order is understood as a spontaneous symmetry breaking of emergent MTC symmetry. But on the other hand, in the fusion surface model, these non-invertible one-form symmetries are exact symmetry on the lattice. And we can discuss spontaneous symmetry breaking of these symmetries. But actually, it turns out that when B is modular, then this non-invertible one-form symmetry has to be spontaneously broken, regardless of the Hamiltonians. And this is because in a modular tensor category, the modularized matrix is non-degenerate. That means that for any topological line A, there exists another topological line B that is charged under the action of the line operator A. So this is just another way to say that the symmetry generated by line operator A is spontaneously broken. So this means that modular tensor category symmetry has to be spontaneously broken by definition. And this implies that there are at least 3 possibilities for the phases realized in the fusion surface models with these symmetries. So the first possibility is a gapless phase. And the second possibility is a topological phase described by this as the same modular tensor category B. And the third possibility is a larger topological phase with emergent anyons. And the simplest example of this third possibility is a non-chiral phase that is given by the product of B and B bar. So in particular, this fusion surface model with a non-invertible one-form symmetry B exhibits a topological order B if the energy spectrum is gapped and there are no other symmetries are spontaneously broken. So from this discussion, it would be natural to expect that the fusion surface models with these symmetries can realize general topological orders in some parameter regime. So it would be interesting to investigate the phase diagrams of these lattice models. But this is still an open problem. So this is an interesting future direction. And I think I'm already running out of time.
No, this is fine. You should just continue because we had lots of questions. But there's another question here. So
Yeah, I have a curiosity. So, I mean, in the case of the anion chain, it's known that you can realize, for example, all the minimal models if you tune the parameters to criticality. No, is there some example of a gapless model that you realize with this construction? Probably no, I don't know. Like, just a curiosity.
I have no examples of fusion surface models that realize a gapless phase for now.
Okay. Okay. That would be very interesting. Okay. Thanks.
Yes. Thank you.
Actually, I have a confusion about the previous slide. Why does the S matrix imply that this mod B is always boundedly broken? I would have thought it's implying something more like a Tufts anomaly, which then implies that options 1, 2, or 3 are possible.
Yeah, what I mean is that if the moduli matrix is non-degenerate, then for every topological A, there's a charged topological line B. So this means that the symmetry generated by A is spontaneously broken because there's a topological line that is charged under the symmetry. This is all what I mean by what I said.
Okay.
Okay, so finally, let us discuss some relations of the lattice models to topological field series in one higher dimensions, which are called symmetry TFTs. So to this end, we first recall the basic ideas of the symmetry TFTs. So in general, finite symmetry in n dimensions can be identified with topological field series in one higher dimensions and its topological boundary conditions. So what I mean by this equality is that an n-dimensional system with finite symmetry can be obtained by putting a topological field series on a slab and impose a topological boundary condition on one of its boundaries. And here, the bulk topological field series is called a symmetry TFT, and the topological boundary that we impose on the left determines the symmetry of this n-dimensional system. And on the other hand, on the right boundary, we can impose any kind of boundary condition. And this boundary condition is often called dynamical boundary condition because this boundary condition determines the dynamics of this corresponding ND system. So in this way, we can obtain an n-dimensional system with finite symmetry by using topological field series in one higher dimension. And we can use this construction to obtain the anyon chain model in 1+1 dimensions. So in order to obtain the anyon chain model, we use a three-dimensional symmetry TFT, which is a three-dimensional trivial topological field series constructed from a fusion 1 category C. And on the left boundary, we impose the Dirichlet boundary condition. This is the topological boundary condition such that the topological defect on this boundary form a fusion 1 category C. So this choice of the boundary condition guarantees that the corresponding two-dimensional system has a fusion 1 category symmetry C. And on the right boundary, we impose the Dirichlet boundary condition decorated by a specific topological defect network, which is shown here. So in this figure, each orange leg represents a chosen object rho, and each box represents a morphism from rho tensor rho to rho tensor rho. And in this case, the two-dimensional system obtained by this symmetry TFT construction becomes a two-dimensional classical statistical model, which is known as the 2D height model. And the partition function of this two-dimensional height model can be expressed by using transform matrix. So here we choose the imaginary time direction as the vertical direction of this figure, and the transform matrix T hat is a transform matrix in this direction. And here the trace is taken over the vector space H, and this vector space H is the state space of the anyon chain model. And the transform matrix acting on this vector space is represented by this fusion diagram. So this fusion diagram is a minimal unit that constitutes the topological defect network that we draw on the right boundary. So this means that the topological defect network on the right boundary directly determines the transfer matrix of the corresponding two-dimensional statistical mechanical model. And then, by taking the anisotropic limit of this two-dimensional height model, we can obtain the anion chain model. So more specifically, if we choose this morphism phi to be the identity morphism plus epsilon phi, where epsilon is a very small parameter, then the transfer matrix becomes an imaginary time evolution by some Hamiltonian h. And this Hamiltonian turns out to be the same as the anion chain Hamiltonian. So in this way, we can obtain the anion chain model by using symmetry TFT construction. And this is studied by the paper by Asim and Rimon. And we can do the same thing in one higher dimensions. So in order to obtain the fusion surface model in 2+1D, we use the 4D Douglas-Reuter TFT, which is constructed from a fusion 2 category C. And on the left boundary, we impose the Dirichlet boundary condition. And this choice of boundary condition guarantees that the corresponding 3D model has a fusion 2 category symmetry C. And on the right boundary, we impose the Dirichlet boundary condition that is decorated by this topological defect network. And again, the partition function of this 3D height model can be represented by using transfer matrix. And now we choose the imaginary time direction to the direction perpendicular to these plaquettes of the topological defect network. And here the trace is taken over the vector space H0, which is the state space of the fusion surface model. And the transfer matrix acting on this state space H0 is represented by the minimal unit of the topological defect network that we draw on the right boundary. And then the fusion surface model is obtained by taking the anisotropic limit of this 3D height model. So we can summarize the symmetry TFT constructions in low dimensions as in this table. So in 1+1 dimensions, a finite generalized symmetry is generally described by fusion 1 category, and the corresponding symmetry TFT is a 3D Dirac-Viro TFT. And if you put this 3D Dirac-Viro TFT on a slab and impose the Dirichlet boundary condition on the left boundary, and impose the Dirichlet boundary condition decorated by this topological defect network on the right boundary, then the corresponding 2D statmech model becomes a 2D height model. And its quantum counterpart is the anion chain. And similarly, in 2+1 dimensions, a finite generalized symmetry is generally described by fusion 2 category, and the corresponding symmetry TFT is the 4D Douglas-Reuter TFT, and the symmetry TFT construction based on this TFT gives us a 3D height model, and its quantum counterpart is the fusion surface model. So in summary, we constructed a large family of 2+1 dimensional quantum lattice models that we call fusion surface models. And these fusion surface models have finite generalized symmetries described by fusion 2 categories. And these models naturally arise from the symmetry TFT construction. And since these lattice models have microscopic symmetries of anyons, we can naturally expect that these fusion surface models might be natural candidates for chiral topological phases. But this is still an open problem, so further study is needed on this point. So this is the end of my talk. Thank you for attention.
Great, thanks a lot for this nice talk. Maybe I'll start off the questions. So the one of the purposes of the SymTFT, well, there's several, but one is it unifies all the models that are, at least in continuum models, it unifies all of them together that are related by gauging non-anomalous symmetries. Do you understand these lattice models, how you go, say, from these say, 2-back G models to something where you gauge them and you see sort of the rep G appearing? Do you understand gauging of these global symmetries? My question.
I haven't done it in detail, but at least at least schematically, the gauging is just done by choosing different topological boundary.
Sure.
And different topological boundaries should be labeled by different modulo categories over fusion 2 category C. And in the case of 1+1 dimensions, this kind of gauging was described in the paper by Lutens, Delkamp, Ortiz, and Ferstrati. And I think we can do a similar thing in 2+1 dimensions, but I haven't done it yet.
Okay, great. And then another purpose is, of course, that you can determine also generalized charges, right? So the topological defects in the bulk become the charges under these generalized symmetries. In these lattice models, did you look at these kind of things? So the Drinfeld center, like what would be the Drinfeld center topological defects and how they can end and what type of generalized charges they give rise to?
Yeah, we haven't done it.
Okay, there's another question. Nat, maybe you can unmute yourself, please.
Hi, Kansei. Thanks for the nice talk. Maybe this was discussed partially already, but I wanted to ask, like, I was wondering if you could comment on the difference between, for example, this 2-rep Z2 versus just the invertible part, like just this like invertible one-form symmetry. If we put that into your model, what would be the difference?
I think 2-rep Z2 is just a condensation completion of one-form symmetry.
Right. So if I threw away the condensation part, how would that reflect differently in your lattice model?
We obtain the same model.
Oh, it is the same model.
Use condensation defect.
So it does not affect the model in any way.
Yes, you're right.
I see. Okay, maybe
just to make sure I just to make sure I understood that answer. So like if you input 2-rep Z2, you get the same model as if you inputted 2-vec script G, where script G is like kind of a trivial 2 group, but has only Z2 one form.
B square Z2.
That's what you're saying?
Yeah,
that'd be the classifying space, yeah.
The model constructed from vec Z2 is different from the model constructed from rep
Right,
Z2.
that would be a 0 form Z2, and I guess.
Yeah. Here would be like vec Z2 one form. So by Z2 one form, I mean a 2 group.
When the Z2 symmetry is one form.
Yeah, like B square Z2, I think that's what.
I think then we get the same model.
That's kind of, if you get the same model though, these are 2 different symmetries, unless the condensation defects of the 2-rep Z2 are like totally trivial.
And is this Douglas-Reuter TFC also the same in 4D with these 2 inputs?
That was the question I was asking, right? Because it should be. So you just change the boundary conditions. It should be the same bulk sim TFT, but then you should see how you go from 2-vec Z2 to 2-rep Z2.
Sorry, maybe I misunderstood the question. Are you asking?
No, I'm sorry. I meant between this B square Z2 to 2-rep Z2. Is this bulk TFT also the same? Like the one without the condensation completion?
I mean, the input is a fusion 2 category, right? Without the condensation completion, it's not strictly a fusion 2 category. So I'm not sure if the question makes sense.
I see.
Yeah, without condensation completion, the category is not the fusion 2 category.
I guess because for like this B square Z2 in principle, you can do this Walker-Wang like Crane-Yetter construction and also get a 4D TFT, right?
Yes.
Yeah, so I'm just wondering if these 2 are related somehow.
In the construction of TQFT, we do not use a full data of fusion 2 category because we do not use condensation defects. Sorry, maybe I couldn't understand the question.
Oh no, it's just open-ended. So yeah, anyway, thank you.
Okay, are there any more questions for Kansei? If not, then maybe we'll thank him again and I'll stop the recording.